So as been mentioned, and today I'm going to talk about semiconductor nanostructures for optoelectronics applications. In addition to being at the Australian National University, and so let me see if I will avoid. So in addition to being at the Australian National University, and I also have honorary appointments in India, Japan, China, Taiwan, US, and UK. It's really a pleasure and honor for me to really be associated with these institutions, and I really want to thank them for inviting me to be working in their institutions. So before I proceed further, I would like to acknowledge my collaborators, and really this is a collaborative effort between my group at the Australian National University and many groups in Australia, US, UK, China, Korea, Sweden, Italy, Russia, and Switzerland. So the beauty of science is there are no national boundaries. We can all work together. And so I really want to thank all my colleagues and many students and postdocs, those who really worked in these groups and then for our collective research. And the beauty of science is I always enjoy working with colleagues because collaboration is great fun. So this is my group at the Australian National University, and then typically 10 to 12 nationalities at any one time. And it's a bright young people, and it's a really pleasure for me to work with them. And I also have got my colleagues, those who really lead the research programs in the group and work closely with the students as well. I want to thank them for their leadership as well. And also the funding agencies for the funding, providing a support to that one. And so without that support, and will not be able to do the research which we are doing. It turns out that I have got one student currently from Kerala, and this is Ashwini Gopakumar. She is from Cochin, University of QSAT, and the Photonics department there. So here is an overview of my talk, and I'll really give you the motivation why we're interested in nanowires and nanostructures. And I'll talk about how do we grow these ones. And then I'll talk about wide variety of optoelectronic devices which we have been working on, and I'll draw some conclusions. Before I proceed further, I would like to thank many groups, those who are working in this field in various parts of the world. And the science, in science, we learn from each other. And then knowledge has been built based on the contributions made by other researchers. It's very important for us to really acknowledge other groups, those who are working in our fields. I want to thank them for enriching our field. So before proceeding about optoelectronics, and let us look at the technological revolutions which have transformed the society. In the first industrial revolution, then the steam power has led to mechanization. Second industrial revolution, electrical power led to mass production. Third industrial revolution, computer power led to the automation. And fourth industrial revolution, people are predicting that the digital and biological worlds will come together. And then the light is going to play an important role and to sense and interface humans and machines. And in view of the fact that about 80 to 90% of the information which we receive is through light, for example. So that's why really the light-based technologies are going to play an important role. Currently, the light-based industries are about 1 trillion Australian dollars, or about 750 billion American dollars. People are predicting by 2030, these industries or the technologies will be doubling in terms of their impact. So that really tells you that there's a real need for photonics and optoelectronics, and then optics-based technologies need to be developed for the future of the fourth industrial revolution. So also in 2018, World Economic Forum has identified many needs of the future of the society. And so some of these things have identified are the holographic displays, wearable optical sensors, and then LiDAR and the light navigation and communication, and 3D vision and gesture recognition, and enhanced machine vision and augmented reality. So all these technologies require smart miniaturized optical systems, and that's what we are trying to do as part of a new Center of Excellence on Transformative Meta-Optical Systems funded by the Australian Research Council, in terms of generating light, manipulating light, and detection of light, and using nanostructures to really generate light, and then manipulation of light using meta-optics, and detection of light using nanostructures as well. And then this particular center has been led by my colleague, Professor Dragobet Neshev. And we got about 15 chief investigators, and with 5 universities in Australia, about 10 to 12 universities where we got partner investigators as well. This is a website for this particular center. Please keep an eye on this one. In the future, we may advertise for PhD positions and postdoctoral fellowships, and hopefully, you'll be able to apply for those ones. So nanotechnology, when we talk about it, nanostructures, and what is so special about nanostructures? It turns out when you go to the nanoscale, and so really, nanotechnology itself is engineering at the atomic and molecular scale. When you go to the nanoscale, the surface area becomes quite significant with respect to the volume of the material. So that means these surface properties can be exploited for catalysis and sensing and hydrogen storage using carbon nanotubes and lightweight and high-strength materials. The second thing which happens is a quantum size effects come into picture. So essentially changing the size of the nanoparticles, or the quantum dots, which we call it, essentially you can be able to really get different colors of light by if you excite them with the UV light source, for example. So that the classical physics, I cannot explain how by essentially changing the semiconductor size can be able to get different colors of light. But once if you really bring in the quantum physics and you can really solve the Schrodinger equation and a particle in a box, you should be able to explain how the different colors of light been emitted by these so-called quantum dots, for example. And already we are seeing in the quantum dot TVs available in the marketplace because of their high brightness and their sharp light emission as well. Optoelectronics, and of course, you're a department of optoelectronics. I don't have to tell you what is optoelectronics. So a simple definition is that the conversion of light into electricity, and using solar cells, for example, and photodetectors, conversion of electricity into light using LEDs and lasers, and which could be used for a range of applications. So as you know that the silicon is a wonderful semiconductor. In fact, silicon is now widely used also for silicon photonics. But unfortunately, silicon is not a very good light emitter because of its indirect band gap nature. That means the minimum in the conduction band and the maximum in the valence band in silicon is taking place at two different wave vectors. But unfortunately, for light emission purposes, you need to really have direct band gap semiconductors. That's where we end up using group 3-5 semiconductors for the periodic table: gallium arsenide, indium phosphide, gallium nitride, aluminum nitride, gallium antimonide. And these different materials have got different band gaps. So that means they emit and also absorb different colors of light, for example. Okay. So in fact, the developments in the nitride technology has led to the blue LEDs, which has led to the Nobel Prize for these 3 Japanese scientists, because the blue LED was a missing link. We already had a red LED and a green LED using these materials. But without the third primary color, it was difficult to make white LEDs. But now it's been developed, all 3 LEDs are available. People are able to really make white LEDs, and in fact, all the LED lighting and various places, and also large area displays, they're all due to the developments in the LED technology. The materials which are used for making LEDs could also be used for making lasers, for example. Okay, the same materials. And then the same materials could also be used for detectors, for example, infrared detectors, and for night vision applications, and also biomedical imaging applications, and also manufacturing applications as well. Also today I'm able to talk to you because of internet and optical fiber communications. The electrical signals from my computer have been translated into optical signals using lasers. Using a modulator, will switch on and off and send the information, and through the optical fibers, and they get amplified using the optical amplifiers. And on the other end, you're converting the optical signals into electrical signals using photodetectors or photoreceivers. So in this case, then most of these signals are really transmitted at the 1.3, 1.55 micron wavelength region, because those are the wavelengths where you got the lowest absorption and dispersion is taking place. And then the lasers and detectors are made out of these aluminum, indium gallium arsenide phosphide materials, which we work on as well. So nanowires. Nanowires are seen as building blocks for the next generation electronics and photonics. What is so special about nanowires? So it turns out that you do not have to worry about the lattice mismatch. So whenever you talk about lattice, crystal lattice, we are talking about the unit cell. So unit cell is nothing but basically a lattice constant is the size of the unit cell. It repeats itself in a crystal. So then when you're really trying to grow two-dimensional materials, you always have to worry about what is the lattice constant of the layer which you're depositing, what's the lattice constant of the substrate you're really depositing. If there's a huge lattice mismatch and then the layer really relaxes back its original lattice constant, it ends up creating a lot of dislocations. So those materials are useless as far as optoelectronic devices are concerned. But whereas if you really take the nanowires, and because of their nanoscale and the three-dimensional nature, either they can expand or contract depending on the lattice constant of the material with respect to the substrate without creating dislocations in principle. So that is a property which we are really trying to exploit to be able to say, for example, integrate the 3-5 semiconductors with silicon, which has been the dream for many years, but the defects have really limited the performance of these devices. But our hope is that by using these nanowires, we'll be able to bring both silicon and 3-5 semiconductors together. And we and many groups are working in this area, for example. Also, you can make within the nanowire various different materials. This green material is different than the red material. So that means you can create quantum dots or quantum wells within the nanowire. You can also dope these nanowires and make PN junctions. You can also create radial quantum well structures or core shell structures, for example, which I will come back to. Also, you can create branch nanowires. Really opens up opportunities for us to be able to make three-dimensional architectures. You can see that, in fact, these are some of the results from my own laboratory where we have shown gallium antimonide can be grown on top of gallium arsenide. Despite large lattice mismatch, you are able to show that you can get atomically perfect gallium antimonide, which is a very important material for infrared applications. You can also create a branch nanowires of indium arsenide on top of gallium arsenide. So that means they could be used as cantilevers and scanning probes or so. We have also demonstrated nano trees of indium phosphide, which is very good for energy harvesting applications, particularly for hydrogen generation, for example, which I will come back to. Also, we are moving from nanowires to nanomembranes and nano rings and other things, which I will come back and then share with you. Of course, people have been using these nanowires, have been demonstrating LEDs, lasers, photodetectors, biosensors, and solar cells, which I will share with you some examples. But most importantly, recently the IBM Zurich has also demonstrated indium gallium arsenide nanowire transistors on 6-inch wafers of silicon, indicating that in the future, nanowires also will be used for electronics applications as well. So if the nanowires are so much of importance, how do you make these nanowires? So the two main techniques which we use, one is called as a metal catalyzed VLS growth process, and another is called as selective air epitaxy, which I will share with you what these things are. And we use a technique called a metal organic chemical vapor deposition, or MOCVD. There's also an alternative technique called MBE, molecular beam epitaxy. Because MOCVD is used by industry, then we've chosen to really go for MOCVD, for example, so that technology could be transferred to industry much more easily. So in this case of this metal catalyzed VLS growth process, we take some nanoparticles of gold, which you can commercially buy these things in a colloidal solution these days, as small as 5 nanometers, as big as 300 nanometers or so. We put a droplet of this colloidal solution, and so then we try to put this one into the MOCVD reactor and heat it up. It turns out that it is put on a gallium arsenide substrate, for example. Gold has got a melting temperature more than 1000 degrees Celsius, but once the gold starts reacting with the gallium or aluminum or indium, the alloy has got a melting temperature as low as 350 degrees Celsius. So now if you take this wafer and then heat it up in a MOCVD reactor to somewhere between 370 to 500 degrees Celsius, introduces the gases needed for the growth of gallium arsenide, for example, trimethyl, gallium, and arsine. These gases get incorporated into this liquid alloy. It gets supersaturated, crystals start precipitating out, and gold is always sitting on the top, for example, here. Okay. This is like if you're dissolving sugar in the water. Of course, this sugar starts dissolving till the solubility limit. If you excite the solubility limit, and then the crystals start precipitating out, exactly the same physics is happening here as well. In fact, here is an example of the case of this is the work of my former student, Dr. Hannah Joyce. During her PhD, she worked at the ANU. Now she's an associate professor at Cambridge University. She developed a technique called a two-temperature growth process, and thereby we were able to really demonstrate excellent quality gallium arsenide nanowires, for example, here. You can see these are using the 50 nanometer gold nanoparticles, and we're able to make these beautiful cylindrically shaped gallium arsenide nanowires, using this 2-temperature growth process. Lots of times, nanowires are always tapered. And then by using this 2-temperature growth process, starting the growth initially at a high temperature to nucleate it, and then reducing the growth temperature later, you reduce the lateral growth and you end up getting these beautiful cylindrically shaped nanowires, which are important for making lasers and other devices. You can see the transmission electron microscope image. Then this one is a gold nanoparticle, and here is a gallium arsenide, which is absolutely atomically perfect. Okay? And particularly, now if we don't use this 2-temperature growth process, we were seeing earlier this lots of twin defects and other things, and we were able to get rid of all of them. They're very good for making optoelectronic devices, like lasers, which I will come back to. In this case, we use something called selective epitaxy. In this case, by the way, VLS is vapor liquid solid growth mechanism. You're incorporating a vapor into a liquid and getting a solid, and Wagner and Ellis and Bell Labs have introduced this terminology called VLS growth process. So the selective epitaxy, in this case, we don't use any metals. We take a semiconductor substrate. In this case, I'm giving an example of indium phosphide. We deposit some silicon dioxide using plasma-enhanced chemical vapor deposition, and spin coat some ZEP resist, and do electron beam lithography and create ordered patterns of holes here. And then you etch through those holes, so thereby, and remove the photoresist afterwards. What you end up having is the indium phosphide wafer coated with silicon dioxide, with the holes opened up so that in these holes indium phosphide has been exposed. Then you put this one into the MOCVD reactor, heat it up to somewhere between 650 to 750 degrees Celsius, and introduce the gases needed for the growth of indium phosphide, trimethyl indium and phosphine. These gases dissociate, and the nucleation takes place in these crystals which are exposed here, and then you end up getting this beautiful indium phosphide nanowires here. Because we created ordered patterns of holes here, you also get the ordered patterns of this indium phosphide. You can see the top view of this one, see the beautiful crystal facets and others. So these particular nanowires are about 200 nanometers in diameter. And then this is the work of my former student, Dr. Chian Gao, who is now a research engineer in blue glass in Sydney, for example. Okay? So we've taken these nanowires and then excited them with a laser pulse to generate electron hole pairs, and then look at the light coming out of those ones, so-called photoluminescence. And then we quantify the quantum efficiency as a function of the excitation power. And you can see that you can get quantum efficiencies as high as 50% or so. This red curve, for example, here for indium phosphide nanowires. Also, we compared these nanowires with the epitaxial layers or the 2-dimensional layers which we grow normally. And then the blue curve here, they both are very much comparable, stating that the surfaces, despite large surface area of indium phosphide nanowires, surfaces do not act like non-rate recombination centers, and you can get excellent performance from these indium phosphide nanowires, which are very good for making lasers, LEDs, and then solar cells also, which I will come back to. But that is not the case with all the semiconductors. For example, gallium arsenide case, you end up having a huge amount of non-rate recombination, and then we have to always passivate the surface by coating with aluminum gallium arsenide. Again, I'll come and then share with you. So then we asked ourselves, instead of opening a hole in this mask, what will happen if you open a slot or a ring, and what type of structures we can really get? Again, this is the work of my former student, Dr. Nayan Wong, who is a postdoctoral fellow in the group now. Again, you take indium phosphide substrate, you deposit some silicon dioxide, put some ZEP or PMMA photoresist, do electron beam lithography. So thereby, essentially, you're polymerizing this polymer, and then essentially you'll be able to etch that part very easily, and other parts you don't etch, for example. So you can see that that's what we want to really create in this particular instance. Okay. Again, Nayan Wong has spent about 4 years in optimizing various growth conditions, temperatures, flows, and pressures, and all these things optimized to be able to get a good quality results, for example. So here is a case when a slot is opened along this particular crystallographic orientation, put into the MOCVD reactor, heat it up to somewhere between 650 to 750 degrees Celsius, introduce the gases needed for the growth of indium phosphide, you can start getting these beautiful nanomembranes, for example. And so then if you open the slot along another crystallographic orientation, this particular orientation, for example, here, and again, you do the same process, and again, you get these nice membranes, but these membranes are thicker than these membranes, and you also end up having a different facets on the side walls with respect to these ones, for example. But if you open in between these two slots, orientations, then what will happen is that you end up getting these diamond-like structures with these alternating facets, which I have shown you earlier, 1, 0, 1 bar 0, and 1 bar 2 bar 0 or so. Now you can see, instead of just making nanowires, we can make thin nanomembranes and thick nanomembranes and nano diamonds. Depending on the application, you can make use of these things, for example, nanomembrane lasers, MEMS applications, and a range of applications, for example. So what will happen if you open a ring? If you open a ring, again, you can see that you can create these beautiful ring-like structures with these alternating facets, which I have shown you earlier. Again, Nain Wong has spent a lot of time in optimizing various growth conditions, including temperature and various things. If you keep on growing, what happens is that this gap gets filled up, and then you get this the horizontal membrane here. If you keep on growing further, you ultimately finish off with this hexagonally faceted structure, because these facets have got the lowest surface energy, and then crystals always like to be in the lowest surface energy, generally. Okay. So Nain Wong has taken these structures and did something called cathodoluminescence. Cathodoluminescence is an alternative technique to the photoluminescence. These things are done in a scanning electron microscope. You excite these nanostructures of the nanomembranes and the nanodiamonds and nanorings with an electron beam and generate electron hole pairs, and then look at the light emission due to their recombination. You can see that you can get a very bright light emission from all these nanostructures and very uniform light emission, indicating that 4 years of hard work of Nain Wong has really paid off, and then really we were able to show that you can get excellent quality nanostructures of wide varieties, not only just nanowires, for example. Okay. So now, of course, we have been using these nano rings, for example, for nano ring resonator lasers, and which I will come back and then share with you. So till now, I've spoken about materials. So now let me talk about devices. Lasers. All of us have studied about lasers, and then we've been taught that you need to have a gain medium, you need to have a laser cavity by putting some mirrors, and then you need to pump the gain medium to create the population inversion. And as and when the modal gain is equal to the optical losses in the cavity, the lasing starts taking place. These are undergraduate optics courses all of us have studied. In fact, this equation essentially is saying the same thing as what it's showing here in the schematic. Gain need to be equal to the internal optical losses and mirror losses, then only lasing starts taking place. If you take nanowires, if you shine light from the top, for example, light starts propagating along the nanowire, because nanowire acts like a waveguide. Of course, if you choose the right kind of nanowire. But also both ends of the nanowire acts like mirrors because of the large refractive index between the semiconductor 3.4 and then the air, which is 1, for example. So now you can see, if I really choose the right kind of nanowires, and each nanowire can act like a gain medium and forms a nano cavity, and you got the mirrors at the both ends as well, I really don't have to do anything else. And I can excite that one and then look at the light coming out of those ones also. So because these compound semiconductors are direct band gap semiconductors, intrinsically have got the gain as well. Okay. So we've been working in this area for a long time, and in fact, we've demonstrated a wide variety of nanowire lasers. And Dr. Drew Saxena who is now at Imperial College, has demonstrated gallium arsenide nanowire lasers. Dr. Qian Gao has demonstrated woodsite indium phosphide nanowire lasers. And again, Dr. Saxena has demonstrated quantum well lasers. And also Dr. Tim Burgess has demonstrated zinc-doped gallium arsenide lasers, who is at IP Australia now. This particular nanowire work was led by Dr. Sudha Mokkapati. In fact, she has her master's degree from University of Hyderabad in physics, and then her MTech in material science from IIT Kanpur as well. Because Professor Desai and Professor Nair has been talking about IIT Kanpur, I just want to share with you. She was my former student and later on a young scientist in my group. Now she's an associate professor at Monash University. I want to thank her for leading this particular program during our group, staying in our group. So Drew Saxena has gone and did some simulations using something called FTTD simulations, essentially solving the Maxwell's equations. So looking at how the light propagates through these nanowires, and then looking at various optical modes which are propagated to these ones. And here's an example of the TM01 mode, which has been propagating through gallium arsenide nanowire, which is about 260 nanometers or so. We've also looked at a wide variety of other modes, which I will come and then share with you. So what Drew Saxena has done is he has plotted the threshold gain for lasing as a function of the diameter of the nanowire for a nanowire of about 10 microns long. And you can see that they are dependent on the optical mode, and also that the lowest threshold gain for lasing is for the nanowires, which are about 250 to 300 nanometers or so. So you can see, in fact, I'm not plotting from 0 here, starting from 150. If I use, for example, a 50 nanometer nanowire, it may not be a very good waveguide. And then also the threshold gain for lasing is so high, before you can able to get any lasing, you may exceed the threshold damage for materials damage threshold. In the process, you may burn and then also melt these materials as well. So that's why we started really looking at nanowires which are 250, 300 nanometers in diameter or so. This indicates to you that the simulations really play an important role, and when you're really designing these nanowire structures and nano lasers and wide variety of nanoscale optoelectronic devices. Again, he calculated the peak gain as a function of the injected carrier density. You can see threshold-like behavior. And again, the amount of carriers you need in order to be able to get over the losses is dependent on the temperature of the device as well. That's what you would expect as well. Okay. So based on the simulations of Drew Saxena, another student, Dr. Jenny Jiang, who is now in Cambridge University, she has grown these gallium arsenide, aluminum gallium arsenide core shell structures. These are about 6 microns long nanowires. We transfer them onto a glass slide, and Drew Saxena did the measurements. And you can see that if you pump these nanowires and look at the light coming out of these ones. Below threshold, you see a very broad light emission, or here, for example. And above threshold, you see a very narrow line emission, which you would expect for a stimulated emission for a laser. You also see the above threshold a beautiful interference fringes. In fact, Drew Saxena has done simulations for this particular laser, how the interference fringes will look like. And he was able to compare these things really very nicely. And again, output versus a pump intensity, you can see nice threshold-like behavior. Here it is spontaneous emission or acting like a light-emitting diode. In this region is amplified spontaneous emission, and here is a spontaneous, the stimulated emission is taking place here, for example. Again, we plot the output versus input as a log-log plot, which really shows this S-type curve confirming this true lasing is taking place. These are the first gallium arsenide nanowire lasers operating at room temperature, optically pumped ones demonstrated in the world, for example. And Drew Saxena was able to publish this work about 8 years back now in Nature Photonics also. So then what are we doing with these nanowires lasers? This is a collaborative work with my colleague, Professor Martin Dawson's group at University of Strathclyde. They developed a technique called nanoscale transfer printing technique. They come up with a PDMS stamp. They can pick up the nanowires and then drop it wherever you want, precise nanoscale location of these structures, for example. A research fellow, Dr. Benoit Gulhebert, has spent a lot of time in their group, and along with Professor Antonio Hurtado and Professor Michael Stein as well, in developing this particular technique. So here is a case where they transfer these nanowires onto flexible glass substrates, because flexible glass, we want to use it for sensors and flexible optoelectronics applications. You can see the optical image of these 4 nanowires and 3 nanowires and 2 nanowires here. And again, they pump them with a laser and then look at the light coming out of these ones. You can see the light is coming from the both ends of the nanowire. And essentially, a nanowire is acting like a Fabry-Perot cavity. And you can see the output versus input characteristics. And you can see a threshold-like behavior. The stimulated emission and lasing is taking place here. He's acting like a light-emitting diode and a narrow line width also, indicating that this transfer process is a gentle process. We have not created any damage during this transfer process. That's an important thing. If you do develop some technique, if you are damaging your devices, you really can't use it for optoelectronic device applications. They've also transferred them onto in front of this Y junction. This is a polymer SU8 waveguides for multiplexing and demultiplexing applications. You can see the close-up of this one. Is a 1 nanowire is here, 1 nanowire is here. We pump these ones and look at the light coming at this end here, so that we can use and demonstrate that we're able to show that you can use them for multiplexing and demultiplexing applications. You can see this light on the other end of this particular devices as well. This is the work of the PhD student in University of Strathclyde, Dimitar Geotics, and again, he spent a lot of time in optimizing and demonstrating these results as well. So then we asked them, can we be able to really place these nanowire lasers in nano antennas using this transfer printing technology. This is the work of my young colleague, Professor Fang Ren. Now she is back in China in Nanjing University as she's a full professor now. She has been working on something called terahertz metamaterials. She has been making these so-called bullseye antennas, ordered patterns of these bullseye antennas. And here is the aluminum antennas which have been fabricated. In the middle, there's a gap. We requested them, can you be able to locate these nanowires in the gap here? You can see the close-up of this particular structure. You can see this nano antenna here and then the nanowire here. If you do not have any nano antenna, if I excite this nanowire, what will happen is that light is coming from the both ends of the nanowire. It acts like a fabricator cavity, as I showed you. But whereas if you put the nano antenna, suddenly light is coming from the middle and from the vertical direction is light is coming from. These are vertical emitting nanowire lasers. And again, these are the first room temperature operating vertical emitting nanowire lasers. Again, threshold-like behavior, and then again, narrow line width, indicating that we're able to demonstrate these vertical emitting nanowire lasers also. So now we can see depending on what applications you have, if you want to couple the light to an optical waveguide or an optical fiber, and you make use of these edge emitting lasers and be able to couple the light efficiently. But if you want to have the light to be coming out of the surface of the screen, for example, vertically towards you, and so that means you end up using these vertical emitting lasers, for example, for meta optics applications or also for facial recognition applications and a range of applications, for example. So depending on what you want, you end up designing and then fabricating a particular kind of lasers, for example. By the way, these lasers are really, really tiny lasers, and then we can put about 20 lasers within the width of your hair. That really tells you how tiny these lasers are. Why are we interested in tiny lasers? Smaller the laser, they consume less energy. You can switch it on and off faster. You can pack more lasers. And depending on what applications you have, you can use it for sensing applications and a range of things as well. So now let me move towards these ring resonators.
Professor Jagdish, that means you don't see the light at from the end of the fibers, the nanofiber, when you put it on the antenna?
Yes, that's right. We don't see the end of the fiber. We end up seeing the light coming from the vertical direction.
Okay, yeah, okay.
Yeah. Okay, so that's essentially, we're engineering the radiation patterns, and that's why this nano antenna is essentially doing so.
Yeah, okay, yeah, okay. Yeah.
But it's a very good question, Professor Rao. Thank you. So then we have also looked at, this is the work of my student, Wei Wong. And then again, we looked at these ring resonators, which I've shown you earlier. Again, we designed these ring resonators and various optical modes, which are propagating through these ones. And based on his designs, and again, we grown these ring resonators. And we pump these ones, and you see below threshold, you see the broad light emission. Above threshold, you see beautiful, these whispering gallery modes. And again, you can really compare these simulations with experiments, and they match very well, showing that these ring resonators are very good for making whispering gallery mode lasers, for example. Again, you can see the threshold-like behavior, the S-plot, and then the narrow line width, again, showing that we're able to do this one. So these ring resonator lasers are very good for photonic integrated applications and be able to couple the light to multiple waveguides and other things, and that's what we're really exploring at this stage, for example. So till now, what I've shown you is only optically pumped lasers. I have not shown you any electrically pumped lasers. But ultimately, industry wants to really use electrically pumped lasers, for example. So this is the work of my student, Dr. In-Suk Yang. He's now, he came from Samsung in Korea, and then he returned back to Samsung, where he's a research engineer there. This particular work has been led by my colleague, Professor Lan Fu. So you need to make a PN junction to be able to, a diode, for example, and you need to have a gain medium. So he has spent a lot of time in optimizing the zinc doping. Zinc doping leads to, if you dope indium phosphide with zinc, you get a P-type dopant. And then it grows this indium gallium arsenide quantum well. And you see this yellow one here. And then the N-type indium phosphide by silicon doping. So thereby you're able to create the PN junction. Then you can see the schematic here and actually grown structure, which again, he spent a lot of time in optimizing various conditions. And then he has gone and fabricated these devices by doing electron beam lithography and depositing some metals so that gold titanium at both ends of this PN junction, for example. So and then he injects current and look at the voltage drop. And you can see that the IV characteristics showing that you can see the nice diode-like behavior, indicating that he is able to successfully get the PN junction and also able to make good ohmic contacts as well. So here is the light emission versus the wavelength. you can see that as and when increasing the injected current, and you're able to get the higher, the more and more light emission is coming out of those ones. You also see two emission peaks. That's mainly because the quantum well which is formed on the surface on the top here has got a different thickness and composition with respect to the quantum well which is formed on the side walls of these nanowires here. So that's why you end up having two emission peaks. But also you can see that the wavelengths which we're really dealing with are in the 1.3, 1.55 micron region. So that's the region which the optical communication systems use. That's why we're interested in this. But even though we're injecting more and more current, but you don't see any narrowing of the line width. Also, you don't see any threshold behavior from the output versus injected current, for example. So what it's essentially telling us is that they're acting like a nanowire LEDs, light emitting diodes, not like lasers. So then you ask the question why that is the case, because you got a PN junction and you need a laser cavity. Why? What's the problem? The problem is whenever you put metals to be able to inject current into these nanowires, what happens is that the metals have got a huge optical losses. They create a lossy cavity. Because you got a lossy cavity, you have to pump it harder to get over the losses. Then you generate a lot of heat, and heat reduces the gain peak of the medium and peak intensity of the gain of the medium. So that means you have to even pump them harder. It becomes like a vicious circle or so. Okay. So now we got another student, Nikita Gagrani, who came from IIT Kharagpur, who has been working, in fact, last 4 years in continuing this work, replacing these metals with the indium tin oxide and aluminum doped zinc oxide or the transparent conducting oxides to minimize the losses and still be able to inject the current to be able to get these things to lathe. And still it's been a very, very challenging project. And I'm hopeful in the next 6 months or a year or so, we'll be able to demonstrate this one. Really, really challenging project. So before Insuk leaving our group, and he has also demonstrated nanowire LED arrays. And you can see that these nanowires, which we normally grow in the vertical direction, challenge is how to make contacts to these nanowires. We deposit some, fill this one with the polymer material by spin coating and selectively etch the polymer by using plasma etching so that you can expose the tips of the nanowires and put some indium tin oxide as a transparent conducting oxide, put some metal on the side and then also metal at the bottom. So inject current into these nanowires and look at the light emission. Again, IV characteristics showing that diode-like behavior. As and when you're injecting current, you can see also more and more high intensity of light is coming. In fact, you can see below the probe here, very bright light emission coming off these ones. So why are we interested in these nanowire LEDs? Because of the fact that you're able to now embed these nanowires into a polymer material, you can peel these things off so that they can be used particularly foldable and flexible displays, for example. See, Samsung and Apple and others are interested in foldable phones and foldable computers and other things. So that's why he spent a lot of time in optimizing these conditions, for example. So till now, I've spoken about nanowire lasers and ring resonator lasers and nanowire LEDs. And now let me move towards terahertz radiation. So terahertz radiation really falls between electronics and photonics. In the electronics, we talk about when you go to high speeds, microwaves and radio frequency, and also the millimeter waves. In the optics, we talk about UV light, visible light, and infrared light. There was a gap called terahertz gap for many years. So during the last 20-25 years, and the compact terahertz sources and detectors have been developed by many groups, including we're also involved along with Oxford University. And why people are interested in terahertz part of the electromagnetic spectrum? And many chemical molecules or biomolecules have got signatures that terahertz parts of the electromagnetic spectrum. For example, here is the spectra from the lactose, monohydrate, and anhydrate, for example. Okay? Also, a lot of medical drugs have got also signatures in the terahertz parts of the electromagnetic spectrum. By the way, 1 terahertz is about 300 microns. So the far infrared wavelengths which we're really dealing with here. But the nice thing is also terahertz radiation is reflected by metals, for example. So that means nowadays when you go to the airport, they don't use any X-rays anymore because X-rays really creates a lot of damage because of the high photon energy of these X-rays, for example. And so that's why you end up using is the terahertz radiation, which is a non-ionizing radiation because of the small photon energies of this terahertz radiation. It could be used for biomedical imaging applications, for looking at the cavities in the teeth, and even cancer detection. Wireless communications, where you can download a lot of information from your kiosk, from your smartphone, for example. Also detection of water content in leaves so that you're only watering the crops when they need to be, rather than wasting precious resources like water, for example. Really, terahertz has got lots of applications. So we've been looking at, we have looked on terahertz sources also, in this particular case, using nanowires for terahertz detectors. Again, as mentioned, this work is jointly with my colleagues at Oxford University, Professor Michael Johnson and Professor Laura Hertz. So this particular work is done by my student, Dr. Kun Pang, during her PhD, but now she's a postdoctoral fellow at Oxford University. What we do is that she transferred a nanowire onto a quartz substrate, because quartz is transparent to terahertz radiation so that light can pass through, and terahertz can pass through, for example. And then she made contacts using electron beam lithography. It connects to an ammeter, for example, here. Then we come with a laser pulse to excite the electron hole pairs in the nanowire, and then you come up with a terahertz pulse. The electric field of the terahertz pulse is the one which separates these carriers, and you measure the photocurrent as a function of time. So if you can measure the current as a function of time, you can extract the electric field of the terahertz pulse as a function of time, and also the conductivity of the material which we're dealing with as well. In fact, originally we were really studying the electrical properties of the nanowires using optically pumped terahertz time domain spectroscopy, and that's where we got the idea that can we really be able to detect these terahertz radiation using single nanowires, because these nanowires are typically about 300 nanometers in diameter, about 5 or 6 microns long, but whereas terahertz radiation is about 300 microns in wavelength, for example. So that's a curiosity-driven question which we asked ourselves. So again, to cut the long story short, and then Kun Pang has demonstrated during her PhD, gallium arsenide single nanowire terahertz detectors. These are amplitude and phase sensitive room temperature operating terahertz detectors. Then she demonstrated also indium phosphide nanowire terahertz detectors. But let me share with you the most recent results. And during her postdoc, she has been working at Oxford, along with my group at the ANU, and also Professor Martin Dawson's group at the University of Strathclyde. So in this case, what we are trying to do is that we are trying to develop these polarization resolved terahertz detectors. So what we do is that we take these nanowires, and then of course you got these so-called Bauta antennas, which will be able to couple the terahertz radiation to the nanowires. But in order to be able to measure both X and Y polarization, we had to really create these, orthogonally oriented these nanowires, or 90 degrees to each other. Challenge has been how to avoid contact between the top nanowires and the bottom nanowires. If they're physically in contact, they short circuit the device. So that's where Kun Pang has spent about 3 years in optimizing these things. You can see that the nanowires which are grown by MOCVD at the ANU, and then also you can see these Bauta antennas. And if you go and close up of these ones, she tries to put, instead of using 1 nanowire, she tries to put 2 nanowires in both the directions. So it becomes like a hashtag, for example. Okay. So the challenge is to really avoid the top nanowires to be not physically in contact with the bottom nanowires. So what we are doing is these sorts of polarization detectors is that trying to study terahertz metamaterials. We design a terahertz metamaterial. You send a terahertz pulse through this one. Terahertz pulse is interacting with the metamaterial. It changes the polarization state of the terahertz pulse. So by using our detector, we measure both X and Y polarization of the change state. So thereby you learn about what type of terahertz metamaterial you got, or otherwise what type of biomolecule you got, what about chemical molecule you're dealing with, sort of thing, for example. So here are the fabricated devices, and here is the simulated designed structures of the X and Y polarization transmission spectra, which you would expect based on these particular terahertz metamaterials. And these are measured using the polarization sensitive terahertz detector operating at room temperature, showing that you can see that very much similar to what we designed and what we've got, indicating that these terahertz polarization detectors are very, very useful to be able to study a wide variety of molecules. And again, polarization sensitive, amplitude sensitive, phase sensitive, operating at room temperature. And after all her hard work of 3 years, she managed to publish this work last year in the journal Science. And really, she was really thrilled with that, because she has really spent a lot of time in getting this into work, for example. So really, all the results today I'm showing with you are due to the hard work of many of the students and postdocs, those who worked in my group, in our collaborators groups. And I really want to thank them for their all the hard work which they're really putting in order to be able to do the exciting science. So now let me move towards nanowire solar cells. So all of you know about solar cells, and then we all studied that you need to have a PN junction. You need to make thick enough PN junction to absorb all the sunlight, and then the photo-generated carriers need to migrate the long distances to really be able to contact at the bottom and the top, right? For a thin film solar cell, for example. So when you say that the solar cell is 20% efficient, that means 80% of the photo-generated carriers from the sunlight has been lost to impurities or defects or surface states, for example. But whereas in this case, you can take the nanowires, you can make them as long as you want to really absorb all the sunlight, and you can make the core cell nanowire of a p-n junction, so thereby the carriers do not need to migrate long distances. So really you're decoupling light absorption pathways and carrier collection pathways for the first time using these nanowires. But also nanowires act like an anti-reflection or low reflection losses because of by their distribution of these particular nanowires. And more importantly, nanowires also can act like a light funnels to concentrate the light into the nanowire because of their high refractive index of the nanowire, because generally light likes to stay in the high refractive index medium, for example. Okay. Again, we have done a lot of simulations, FTTD simulations, finite difference time domain simulations, looking at what should be the height of the nanowire, what should be the nanowire diameter, what should be the distance between the nanowire or the pitch between the nanowires, for example. And also we're looking at the carrier generation profile here, for example, photo-generated carriers. You can see that the most of the current has been generated at the tip of the nanowire, indicating that you do not need to really make very long nanowires. About a couple of microns long nanowires are more than sufficient if you're using gallium arsenide or indium phosphide nanowires, for example. We've also looked at the diameter of the nanowires, and typically you need to have somewhere between 150 or 160 nanometers, for example. Diameter to pitch ratio should be around 0.5 to 0.6 or so. You can see the peak is somewhere here. And then again, these simulations are really playing an important role in designing the nanowire solar cells, for example. So the challenge again is how to make contacts. And again, you see gallium arsenide, aluminum gallium arsenide nanowire is a schematic here, the actual grown structure, filled with the polymer, BCB polymer, and selectively etched using plasma etching. You can see the close-up of the structure, nanowires exposed, and then the polymer in the middle here. And then also indium tin oxide, which is coated on the top, and then the metal contacts at the bottom. Indium tin oxide is a transparent conducting oxide, which allows the light to pass through, but also has got a good electrical conductivity as well. Again, to cut the long story short, and some of the best nanowire solar cells have been demonstrated by my colleagues at Technical University of Eindhoven, Professor Eric Bakers and FOM Institute in Eric Garnett's group. And then they've demonstrated efficiencies as high as 17.8% or so, in saying that it's really very, very promising. They've used the top-down approach rather than a bottom-up approach, which we use. But really, the bottom line is that nanowire solar cells have got a lot of opportunity for us to be able to really make use of for enhancing the efficiency of these particular solar cells. What we've been doing is that we're also trying to, because now we have also embedded these nanowires, the polymer material in the nanowires are embedded in the polymer material, and replacing the polymer with organic semiconductors, along with, again, Professor Laura Hertz's group at Oxford University. We are now trying to develop the flexible organic and inorganic nanowire solar cells, so that in the future, we should be able to really provide you backpacks with flexible solar cells where charging your electronic devices, for example. That's our aim, to be able to make these flexible nanowire solar cells for sensor applications and the self-powered sensors for Internet of Things and various things as well. So now let me move to the water splitting to generate hydrogen. So while solar cells are very good when the light is there, sunlight is there, but then in order to generate the energy, they need to have batteries, and batteries could be heavy, and transportation becomes a challenge as well. So that's why people have been thinking about other energy sources, and now hydrogen is seen as a clean energy source, which is storable and also transportable. Like, when you got the liquid petroleum gas, which we're using, able to transport vehicles, and you can use in place of that hydrogen, for example. So this particular work is led by my young colleague, Dr. Shiva Karaturi and Professor Hotan, for example. So what essentially you got is electrolysis, a cathode and an anode. And then, of course, in principle, you can put two metals, and then you apply some voltage, and then be able to really create electrolysis and be able to generate oxygen and hydrogen, for example. Okay? But that means you need to have a voltage source. That means you need to have, potentially you can use a solar cell, for example. But then then that becomes again a constraining factor. So instead of using metals, what you're using is we're using a photoanode, a semiconductor, If you excite this semiconductor with sunlight, again you generate electron-hole pairs. The holes go and then oxidize water and generate protons. Electrons go here and combine with protons and generate hydrogen. So that means you can be able to really generate hydrogen and oxygen in this photoelectrochemical cell, for example. The challenge is finding the right kind of materials. So some of the requirements are, you need to have the band gap such that the redox potentials of water should be within the band gap of the semiconductor. In fact, this is a slide which I borrowed from my collaborator, Professor Zetian Me from Michigan University. You can see that there are many materials, for example, titanium oxide, which also straddles these redox potentials, but it's got a band gap of 3 electron volts. It will only be absorbing the UV light. That means you're wasting all the sunlight, for example. Same thing with the gallium nitride. Again, you can see, but whereas it straddles the redox potentials, but it's only absorbing anything in the UV light or so, and the photon energy is above the UV, for example, in the UV region. Indium nitride is only straddling one of the potentials here, and so, but if we can go for indium gallium nitride, a combination of these two, you can have a band gap of around 2.2 electron volts or so, still be able to really straddle the redox potentials or so. One of the challenges in this business is either the materials are stable but not efficient, or otherwise materials are efficient but not stable. Really trying to find materials which are stable and efficient is our goal. So that's what we're aiming for. So here is the case. This is the work of my student, Mr. Reddy, and then he really looked at gallium nitride nanorods, and again, he's top-down process, he etched these ones, and then look at the photoelectrochemical process. But normally, gallium nitride is very difficult to etch. But even when you're doing this photocatalysis, we found that the stability is not very good, and we had to coat this with a cobalt oxide, which acts like a co-catalyst. So then essentially, by doing that one, we're able to show that you can get a much more stable performance from these particular structures. As I said, that gallium nitride is not an optimum material. We've been using indium phosphide and then also indium gallium nitride and a variety of other materials in order to be able to make highly efficient and also stable the electrodes so that we can use them for photoelectrochemical water splitting applications also. So now let me finish off with the last topic, brain repair. So as you know that all of us have got about 80 billion neurons, and then these neurons form into neuronal networks. This is the work led by my young colleague, Dr. Vinny Gautam, and then she did a PhD from Jawaharlal Nehru Center in Bangalore, and she spent some time at the ANU. Now she's a lecturer in biomedical engineering at Melbourne University. So while she was at the ANU, we asked ourselves, and if there's got a brain damage, essentially you break the neuronal network and you lose some of the functions. Either you cannot move or talk or do something or the other. Can we be able to create a neural patch and be able to make the connections back and be able to give the functions back to people, for example? So that's a big question which we asked ourselves. Again, Vinny has spent a lot of time in optimizing various protocols to be able to grow these neurons, for example, on indium phosphide nanowires. You can see that the many nanowires are here, and you can see the cell body soma, and then these neurites or axons are really following these patterns of these nanowires nicely. You can see some of the dendrites also here on top of these ones very nicely. Instead of using a single neuronal cell, what will happen if you use a multiple neuronal cells? So in this box is the one where you got the indium phosphide nanowires. You can see there are many neurons here. You can see these axons are really following these patterns of these nanowires which we have really created here. On the planar indium phosphide outside here, you can see these neurons are really randomly making connections. There is no pattern here, for example. So what Vinny does is that she does something called calcium imaging. So essentially, she puts a calcium dye. As and when the action potentials have been fired by the neurons, and ion channels are opened up, calcium ions are passing through, and then the concentrations of these calcium ions will determine the fluorescent intensity of the dye which you got here. So it takes a video of this one, and then looks at if this neuron is firing, what's happening to this neuron and this neuron and this neuron and these astrocytes and other things. Tries to create correlation maps, whether these neurons are communicating with each other or not, for example. And she tries to compare these neurons which are grown on nanowires and neurons which are grown on plain glass substrates, which are typically neuroscientists use. So here's a case where when the neurons are grown on glass substrates, and then you can see that the change in fluorescence as a function of the time. you can say that these neurons are firing randomly. There's no correlation in the terms of the time scale, for example, here, for example. But whereas the neurons which are grown on these nanowires, you can see that the change in fluorescence intensity as a function of time, they're all firing at the same time, and you see excellent correlation. In this case, you see very little correlation, and you see excellent correlation, showing there is some sort of a synchronized and correlated activities taking place in this neuronal network, which has been grown on our indium phosphide nanowires. So when he presented his work at a neuroscience conference 3 years back in Melbourne, so they were quite excited about it, and they started asking her, what type of neurons which are growing? And then she said she's using rat neurons. Then they said, why are you wasting your time? How about using human neurons and human stem cells? So now, in fact, we applied for some funding and we got it. And so we are working with the funding from the Dementia Australia Research Foundation and the Gilbar Foundation, working with stem cell biologists and taking the induced pluripotent stem cells from the Alzheimer's patients and healthy people, and then creating the mini brains or brain organoids with and without microglia, and measuring the signaling behavior using the calcium imaging and multi-electrode array measurements at the electrode measurements, and then try to apply the deep neural networks or artificial intelligence techniques to differentiate between healthy neurons and organoids, and then the Alzheimer's organoids, and then so that you can better understand the signaling behavior differences, and with a hope that we'll be able to really help people with Alzheimer's and dementia in the future. Most recently, in fact, we have also been looking at, instead of using microelectrode arrays, and we are developing nanoelectrode arrays so that you can really measure individual neuronal signals. And these nano electrodes have been fabricated by my former student and Dr. Vidar Raj, who is now at Glasgow University. So really, this is a truly multidisciplinary project involving stem cell biologists, neurobiologists, nanotechnologists, and physicists, and also computer scientists or artificial intelligence people. I'm learning a lot about the neuroscience, and really an exciting project, and we're having great fun. With that, in conclusion, nanowires are nanostructures open up opportunities for manipulation of light-matter interaction at the nanoscale, developing new class of lasers and LEDs, terahertz detectors, integration of optoelectronic devices on various platforms, and solar cells and PEC water splitting, and engineering the growth of the neural networks. So really, it's an exciting area. So the key message is, if you really understand how to manipulate materials and matter, and you can be able to design the structures which you want in order to be able to make high-performance optoelectronic devices. That's a key message which I would like to convey here. And so also, as been mentioned, that I'm currently serving as the EIC of the Applied Physics Reviews. And then please keep an eye on this one. You got some major breakthrough results, or you got some exciting review, think of submitting this one. And we only publish select number of papers. Current rejection rate is about 90% or so. So that means think about something major breakthrough. And I've already mentioned about our Center of Excellence on Matter Optics. And again, please keep an eye on this website. And then whenever you're finishing your PhD or looking for postdocs or looking for even PhD positions or so. Since I started my life in a very small village in India and studied in front of a kerosene lamp and lived with my maths teacher to finish my high school, as a gratitude to all of the people, those who helped us in our life, my wife Vidya and I have started an endowment to really support students and young physicists from the developing countries to come and spend some summertime at the ANU, and our endowment supports these ones. And so then unfortunately during the last 2 years, we are not able to really support students to come and visit us because of the COVID situation or so. And I hope in 2023, we may be able to host students, because 2022 is also still looking not so promising because of the fact that these things take time and visa processing is still a bit of a challenging thing. Again, I want to really leave with you something, because there are a lot of students here. You don't have to be rich in order to be able to help other people. There are about 700 African families have no access to electricity. And Solar Aid, if you donate 400 rupees, which is apparently nowadays the cost of a lunch, they really match the donation and then provide solar LED lamps. So as I mentioned to you, I studied in front of a kerosene lamp. It's really very bad for health, and also you get very little light because of the kerosene smoke. But we'll be able to really create an excellent opportunity for kids to be able to be educated in a healthy environment. Please think of it. There's a small amount of money. You don't have to be Bill Gates or Warren Buffett or Elon Musk or somebody, all of us can do in a small way. Again, we support lots of charities, including Asha India, improving health of education of people living in slums in Delhi. Pollinate Group, which is really empowering women in India and Nepal, providing the solar LED lamps. Kiva for empowering entrepreneurs in 80 countries or so. With that, I want to thank you for your attention.